Today we're going to be looking at how to solve hyperbolic equations. We're going to be predominantly using the inverse hyperbolic functions, which I derived in the previous video. We've got the r-cosh function, which is defined in logs as the natural log of x plus the square root of x squared minus 1. We've got the r-sine function, which is defined as the natural log of x plus the square root of x squared plus 1. And then we also have the r-than function, which is defined as half times the natural log of 1 plus x over 1 minus x. Okay, so I derived those in my previous video. We will be using these all the way through this video. Okay, so hyperbolic equation, let's start simple. Cosh of x equals 2. Now we're going to solve this for x. So we're going to solve it exactly for x as well. We're not just going to get a kind of a long decimal answer. This is why we want the natural log definitions. Okay, so the cosh curve looks something like this. It's got a turning point here at 1 on my vertical axis. And I'm looking for values of x which make cosh 2. So if I draw the horizontal line 2 on there, then we can see we're going to get a positive solution. And then we're also going to get the negative solution. Okay, so there's 2 solutions. And typically there'll either be 2 or 0 solutions for a cosh curve. So we're going to inverse cosh both sides. So that's going to be x is equal to r cosh of 2. So we want the natural log definition of r cosh, and that is the natural log of 2 plus the square root of 2 squared minus 1. So that is the natural log of 2 plus root 3. Now this is a number that is bigger than 1, which means when you log it, it's going to be positive. So therefore that is this root here. And by symmetry, the negative must also be a root of the equation. So therefore the solutions to the equation are plus or minus the natural log of 2 plus the square root of 3. Okay, I'm going to leave it like that. We can't simplify that any further, so we just leave it alone. Okay, that is well, those are the exact answers to this problem. Okay, similar one. This time at cosh x equals 1.25. Again, it's a number that's bigger than 1, so we're going to get 2 solutions. Okay, draw the horizontal line again. Going to get a solution there and a solution there. So 2 solutions, one positive, one negative. I'm going to plug them back through the same formula. So x is going to equal r cosh of 1.25. That means the natural log of 1.25 plus the square root of 1.25 squared minus 1. And I chose this number for a reason. 1.25 squared is 5 quarters squared, which is 25 sixteenths. Minus 16 sixteenths, that leaves 9 sixteenths. So when you square root it, you get 3 quarters. So we've got 5 quarters plus 3 quarters, which is 8 quarters. So we get log 2. Okay, and of course you can run that through the calculator. 1.25 plus the square root of 1.25 squared minus 1. There we go, 2. So the natural log of 2, that is obviously just the positive root here. We've got a negative root as well. So the solutions to the equation are x equals plus or minus the natural log of 2. And it's always worth checking these answers. So let's just check the answers to question number 1 first. So what I'm going to do is just type in log of 2 plus the square root of 3. So that's now stored as ANS in my calculator. And I'm going to run that back through the original equation. So on this calculator, I need to push option. And then I need to go across to the right. And then I have hyperbolic, which is F2. And there's my cosh function, F2 again. So cosh, and I want to cosh my answer. And I should get an answer of 2, which I do. So that confirms that at least the positive root is correct. And if I actually go up here and change that for a negative and run it through again, I still get the answer of 2. And then here, I'm going to change the answer to just log 2. And I should get 1.25 out. There we go. Okay, and again, you could check the negative root if you wanted, but cosh is an even function, so if you change the sign of the contents, it's not going to change the output. Okay, so that's the first 2 examples. Let's have a look at a shine example. Oh, that's the wrong order. Let's try this one first. There we go. So we've got a shine example now. Shine of x is 4/3. Just like we did with the previous example, we're going to use the r shine function this time. So x is r shine of 4/3, and its logarithmic definition is the natural log of x, the input, plus the square root of x squared. This time I'm going to get +1, like so. Again, 4/3 was chosen nicely so that we get 16/9 plus 9/9 is 25/9. So this is just 5/3. So 4/3 plus 5/3 is 9/3. So that is the natural log of 3. This time it's not plus or minus, and we can see that by considering the graph of shine. It looks something like that. Shine is a 1-to-1 function. It's only going to have one input for any given one output. So if we've got an output of 4/3, then it's only going to have one solution, which is the natural log of 3. So don't write plus or minus for this one. That is the only answer. And again, we can check that by running it back through the calculator. So the natural log of 3, let's store that in my calculator. And now I want to do the shine of that number. And there we go, 4/3. Comes out as my answer. If I change the sign of the input, that's going to change the sign of the output. So therefore, negative log 3 is not a solution to this equation. So log 3 is the only solution. Okay, let's have a look at some more complicated ones. So we can get quadratic hyperbolic equations. This one says to use this identity to solve this equation. If it says to use an identity to solve an equation, you must use the identity to solve an equation. You cannot use exponential form. Okay, so let's run this through. At the moment, we have a quadratic shine term, we have a linear cosh term, and we have a constant. So because we have a linear cosh term, I'm going to transform this equation into a quadratic in cosh by using this identity up here. So I'm going to replace the shine squared with something to do with cosh squared. Okay. So using the identity above, we're going to say that 2 shine squared, but shine squared is cosh squared of x minus 1, minus 5 times the cosh of x plus 4 equals 0. So that's now what my equation has become, and I've used this hyperbolic identity to solve this equation. Multiply it out, I'm going to get 2 cosh squared minus 5 cosh, and I've got minus 2 plus 4, so that's plus 2 equals 0. So that's now quadratic in cosh. So you can factorise it or complete the square or quadratic formula, whatever you need to do. So 2 cosh and cosh. It's going to be a 2 and a 1, minus 2 minus 1 equals 0. Just double check. 2 cosh squared minus cosh minus 4 cosh is minus 5 cosh, and then plus 2. Okay. So this tells me that either cosh of x is a half or cosh of x equals 2. So let's think of the graph of cosh. I've already drawn this once, but let's draw it again. That's the graph of cosh. This point here at the turning point is the number 1. So cosh of x equals a half has no solutions. Technically no real solutions, but you wouldn't be marked down if you just put no solutions. And then cosh of x equals 2. Well, actually, we've already solved that one because that was question 1 on the previous page. There's 2 solutions there. And I'm just going to write the answers down because we have already solved that equation. X is going to be plus or minus the natural log of, and it was 2 plus the square root of 3. So those are the only 2 solutions to this quadratic equation. Okay. All right. Again, you can check those. I'm just going to run one of them through the calculator. So the natural log of 2 plus the square root of 3. And I'm going to run it through the original equation. So 2 times shine of my answer squared minus 5 times the cosh of my answer. Minus 5 times the cosh of my answer. And then plus 4, that should equal 0. It does. So that confirms that at least that one is a root. You can plug in the negative to confirm that is a root as well. Of course, this method won't show you if there's any roots missing. You could graph them on the graphical calculator to see that if you needed to. But at least this algebra says that there's no other solutions. So I'm going to move on from that. Okay, now we want question 5. Okay, so question 5 is now a more complicated hyperbolic equation. We've got a sine of x and a sine of 2x. So I've got 2 different ways to solve this one, and I'm going to show both of them in this video. So this one is going to be using a hyperbolic identity to solve it, which you may have been asked to prove is true in a previous part, or you may just be given it, in which case you can use it. But you don't need to know the hyperbolic identities, and you're not given them either. So you may not choose to go down this route. This one is using the exponential definitions. This can get a little bit messy, but in this specific example, it's actually not too bad. Okay, so let's look at the hyperbolic identities first. So the hyperbolic identity I'm going to use is that sine of 2x is exactly the same as 2 times sine of x times cos of x. I have done a whole video on hyperbolic identities already. You do not need to know them for this course, but don't be disillusioned in thinking that there's a trig identity that looks exactly the same, because there's not a perfect relationship between the trig identities and the hyperbolic identities. Just be careful with that. Okay, so now I've got this identity here. I'm going to take this definition of sine of 2x and put it into here. And then that's going to give me an equation which I can solve a bit more easily than is currently stated. So that's going to give me 6 times sine minus 2 times sine times cos equals 0. Tempting to divide by sine at this point, but you should never divide by a variable, just in case that variable is over 0. Always factorise it out. So I'm going to get sine into, I'm also going to divide by 2. So that's going to be 3 minus cos equals 0. Okay, I'm using shorthand notation. S is sine and C is cos. So I've divided by 2 and I've factorised out the sine. So either sine of x is 0, in which case x equals 0. You can use the inverse sine function on the calculator for this one because it's a nice easy one. Or you can just think about the sine graph. Or cos of x equals 3. And for this one, we are going to use the logarithmic definition for our cos. So x is going to equal plus or minus the natural log of x plus the square root of x squared minus 1, which is root 8. Which I'm actually then going to write as x is plus or minus the natural log of 3 plus 2 root 2. Okay, so we've got 3 solutions. We've got x is 0, x is the natural log of 3 plus 2 root 2, and x is the negative natural log of 3 plus 2 root 2. Okay, there's 3 solutions there. All right, exponential definition. It's a different method. You don't have to follow either of these, but sometimes a question will say to use a hyperbolic identity, in which case you must use this route. This one, some people prefer, particularly if you've got a good quality GDC, which will allow you to solve high order polynomials. So what I'm going to do here is I'm just going to jump straight to the exponential definitions for sine. So sine of x is e to the x minus e to the minus x, all divided by 2. And then sine of 2x is e to the 2x minus e to the minus 2x, all divided by 2. And that's going to equal 0. This is a polynomial equation in e to the x. So we're going to have a go at solving it. First of all, I'm going to times the whole equation by 2. In fact, I'm going to times the whole equation by 2e to the 2x. That'll get rid of all my fractions and all of my negative indices. So that's going to give me 6e to the 3x. It's going to give me negative 6e to the x. It's going to give me negative e to the 4x. And then it's going to give me positive 1 equals 0. Okay. I'm going to times it all by negative 1 just so it's a positive polynomial. So I'm going to get e to the 4x minus 6e to the 3x plus 6e to the x minus 1 equals 0. Okay, so at this point, you might spot that e to the x equals 1 and e to the x equals minus 1 are solutions. But it's not very easy to spot. So what I'm going to do is I'm going to use my equation solving mode in my calculator, which actually the FX991 series has this as well. So I'm going to go to equation solver. I'm going to solve it as a polynomial, so it's f2, and it's a degree 4 because it's a quartic. So, and I'm going to type in my coefficient. So the coefficient of x to the 4 is 1. Coefficient of the cubic term is -6. There is no quadratic term, so that's a 0. Then I've got a linear term which has a coefficient of 6 and a constant which has a coefficient of -1. And then these are the 4 solutions that the calculator has given me. 2 of them are nice integers, the other 2 are irrational. So what I'm going to do is I'm going to combine these 2 solutions and factorise out that quadratic from this quartic. So I know that e to the x plus 1 is a factor, and e to the x minus 1 is a factor of this quartic by the factor theorem, as they are roots of this quartic, which means that the product must also be a factor. So that's e to the 2x minus 1 must be a factor of this quartic, and that leaves e to the 2x plus 1 over that side. So the linear term then, I want 6e to the x. I've got a minus 1, so it's got to be minus 6e to the x in there. Check the quadratic, plus e to the 2x minus e to the 2x, there's no quadratic term, so that's good. And then check the cubic, that's minus 6e to the 3x, which is what I want. So that is a good factorisation. This left-hand bracket here is going to yield that e to the 2x equals 1. So that tells me that x is 0, which is this one. This one here, we are going to use the quadratic formula for. So e to the x equals minus b plus or minus the square root of b squared minus 4ac all divided by 2a. So I get x is equal to the natural log of 3 plus or minus 2 root 2, which is actually the same as those 2 answers there. So it doesn't matter which way you do it. Okay, exponential form in this case has worked out okay because of these nice rational factors, and hyperbolic identity worked out quite nicely as well. Okay, both methods gave us the same answers. Right, I've got 2 more examples. This one's another short one, but now we're going to look at the r-than function. So we've got than of x is 4/5. So what I'm going to do is inverse than both sides. So r-than of 4/5. And we have a logarithmic definition for r-than, and that is a half times the natural log of 1 plus the input, which is 4/5 in this case, divided by 1 minus the input. So we end up with that. So that's a half times the natural log of 9/5 divided by 1/5, which is 9 if you cancel the fifths. And then I can use a log law to say, well, that's actually just the natural log of 3. And again, I can check that answer on my calculator, and you should. The natural log of 3 stored in ANS in my calculator. Go to my hyperbolic section. Than of that answer gives me an answer of 0.8, which is, of course, 4/5, which is what the question wanted. Okay. Again, than of x is a one-to-one function, just like the shine function was. So it looks like this. So there is only going to be one solution. Okay. There's the number 1, and there's the number -1. So I want than of x to be 0.8. So there's only one solution. Okay. Right, and final example number 7. Okay, this is a quadratic equation, so we could use again 2 different methods. We could use the hyperbolic identity, or we could use the exponential definition. I'm going to do both. Why not? Okay. So the first thing I notice is I've got a 1 kicking around out here. That's blocking me from doing a lot of things. For example, if that 1 wasn't there, then I could factorise out the shine. Or if that was a cosh squared, then I could just divide the whole thing by shine squared, give me a quadratic in than. But that 1 is a bit of a pain. So I'm going to get rid of that. And the way I'm going to get rid of that is I'm going to say that cosh squared minus shine squared is 1. So I can either plug that straight in, or I can pull off a shine squared from here and then replace that with cosh squared. Either way, using this identity, I end up with 2 times shine squared minus 3 times the cosh of x times the shine of x plus the cosh squared of x is going to equal 0. So now I don't have a term which doesn't contain 2 hyperbolic functions. Okay. At this point, I'm now going to factorise. Now there are different ways you could do this. You could just factorise it as it is. I could divide the whole thing by shine squared, and that will give me a quadratic in than, which I could then solve that instead. It doesn't overly matter. Let's factorise it as it is. So 2 shine and a shine to give me the 2 shine squared. Got a cosh squared here, so they're both going to be cosh, and it's negative, so I want a negative in there. Check the middle term. I've got minus 2 cosh shine minus cosh shine. That is minus 3 cosh shine. So that is a true factorisation, which is nice. If it didn't factorise, then you'd have to divide by shine squared and solve the quadratic for than. Okay, so if this is going to be 0, then that means that one of these brackets must be 0. So if we look at the left-hand bracket, that means that 2 shine of x is going to equal cosh of x. And we can divide both sides by cosh and 2 to give us that than of x equals a half. Or we have this one here, which means shine of x equals cosh of x, and that means that than of x equals 1. Think of the graph of than. And this is where your knowledge of these graphs comes in very useful. It looks like this. We have a horizontal asymptote here at +1 and a horizontal asymptote here at -1. So there is no point on the curve where it is 1, so therefore this has no solutions. So the only solution is going to come from here, and in fact there's only one solution. So we're going to use the logarithmic definition of r than to get our solution. So let's bring that down here. If than of x equals a half, then x is going to equal r than of a half, which by definition is a half times the natural log of 1 plus a half divided by 1 minus a half. The top is 1.5, the bottom is a half, so that's log 3. That is a half times the natural log of 3. There we go. That is the solution to this equation. There are no others. That is the only one. Okay. Right. Let's have a look at trying to solve this using an exponential method instead. So that was obviously using an identity, which was this identity. Let's try using an exponential method. So we've got 3, I'm just going to write it down here actually. 3 shine squared minus 3 times cosh times shine plus 1 equals 0. I've not actually got anything on my notes on this one, so I am kind of winging it, but let's see what happens. So I'm going to replace the shine with e to the x minus e to the minus x. I'm going to square that. 3 times cosh, which is e to the x plus e to the minus x over 2, times shine, which is e to the x minus e to the minus x over 2, plus 1 equals 0. Okay, so there's my exponential equation now. Let's multiply all these brackets. So we're going to get 3/4 out over here. Square the bracket. E to the x squared is e to the 2x. Then we're going to get minus 2, and then we're going to get plus e to the minus 2x. Then we've got minus 3/4. Again, the two 2's are going to combine to bring out the front, just like it did over here. And then I've got this, but then we've got a cross multiple here, got a difference of squares if you like. So that's going to be e to the 2x Then I've got plus 1, minus 1, so they cancel out. And then I've got minus e to the minus 2x. And then I've got my plus 1. Leave it there. Okay. So let's multiply the whole thing by e to the 2x. In fact, let's multiply the whole thing by 4e to the 2x. That will get rid of all my fractions and all of my negative indices. So that's going to give me 3e to the 4x. Okay. The 4's cancelled. 3e to the 4x. Then I'm going to get minus 6e to the 2x plus 3. Okay. And then here again, the 4's going to cancel and the e to the 2x is going to combine. So it's going to be minus 3e to the 4x plus 3. Okay, e to the 2x and e to the minus 2x is going to cancel. Minus minus is plus, the 4's gone, so I'm left with the 3. Then I've got plus 1 times that, which is plus 4e to the 2x equals 0. Okay, so there's my polynomial now. Okay, so things simplify. What's nice here is that that term and that term disappear, so actually it's not a quartic equation at all. It is just quadratic. Those two combine to give me a plus 6. Those two can combine to give me a negative 2. So that's going to be positive 2e to the 2x, subtract 6 equals 0. And then e to the 2x will equal 3. 2x equals the natural log of 3. And then x equals a half log 3. There we go. So that's the only answer that this method has presented, which is great because we only got one answer from the other method as well. But you can choose either in this case, because the question hasn't specified a particular method to use. You can use either an identity or you can use the exponential definitions of your hyperbolics. All right, I know that's quite a long video. I hope you found that useful. If you have any hyperbolic questions that you are stuck on, then just drop them in the comments below, or check out other websites which can solve them for you. If you have any questions, again, just drop them in the comments. Thank you very much for watching, and check out some other videos that I have on my channel to help you learn content.